This is a basic one. You needed the types of beams. The types of beams means you go for the simply supported beams. Simply supported and continuous beams are so many types of beams are there. The first one is a simply supported beam. The first beam is a simply supported beam. The second one is a fixed beam. Okay, fixed beam. The first beam is a simply supported beam. The second beam is a fixed beam. These two beams are mainly using in our field also. The main one is a simply supported beam. Another one is a fixed beam. The most of the condition we will be analyzed in SCAD also fixed beam and manual also fixed beam. Why I am using simply supported which path? We will go for staircase room. That type of works will choose the simply supported beams. Otherwise, you go for analyze the stat pro or manual or anyone, you will go for the fixed beam like that. Okay. Once you analyze the beam design, you know that the three subjects. You know that the three subject. One is the MOS, another one is a structural analysis. Another one is a structural analysis, another one is a DRC. Okay, DRC. The three subjects are known about the analyzing of your beam. The first subject MOS, sorry, mechanics of solids. You know about the bending moment and shear force, deflection, reactions, and all the values. Then structural analysis, you calculated the moment distribution methods and so many types of methods are available. Then finally DRC, you design your beams and columns for your structural elements. Okay, once you go for the beam analysis, you know more known about the MOS subject, structural analysis, then DRC. These are three important subjects to analyze in your single beam. Okay, the first step one, you know about the bending moment for simply supported beam. See, this is our, I draw the simply supported beam. This is our simply supported beam. See this. This is our simply supported beam. This is a A. This is a B. So automatically the simply supported beams only. This is our compression zone. This is our tension zone. You know that I simply draw my cross section for this beam. Okay, this is my cross section. This is a tension zone. This is a compression zone. Okay, you need the simply supported beam. You design the simply supported beams moment only in tension zones. Okay, the moment only in tension zone. You design as a simply supported. The moment only in center portion of the tension zone. So no moment transfer to columns. Okay, the understand this. You design as a simply supported beams. No moment will be transferred to column. Only its moment will be high in middle of this portion. This is called simply support. Next one is a fixed continuous beam. The fixed continuous beam is a maximum we will design in stat same like a manual also. Fixed continuous beam. I simply draw this one fixed continuous beam. See this? This is our fixed support. Assumption as a this is our fixed support. Okay. Assumption as this is a fixed continuous beam. I simply draw 2 meter, 4 meter, 5 meter. Different spans are there. I simply draw my bending moment diagram for this simply sorry fixed end beams. Okay, this is the moment value. This is the moment for your fixed end. You go for simply support only one moment in tension zone. Okay, only one moment in tension zone, but you go for your continuous fixed end, its moments come from compression and tension also, positive and negative moment also in continuous beam. This is a 1 2 3 4 5. Okay, I take this 1 2 portion, take this 1 2 portion, says automatically I draw this 1 2 portion. This is the moment diagram for your fixed beam. Okay, this is the moment diagram for your fixed beam. See this, the moment comes under compression zone and tension zone also. It's three moments it's come. This is a moment, this is a moment distribute diagram. This is our moment also, center zone also moment, the end zone also moment. You compare with simply supported, the simply supported only on mid portion, but you go for fixed beam, it's under the three moment. This end will be comes under moment in top zone, This is our understand easy concept. This is a top zone. This is a bottom zone. Okay, this is a top zone and bottom zone. You go for fixed beam. This end. This is our I cut this cross section. A. This is a center cross section. B. This is center cross section. C. Okay, three cross section. I go for A cross section. My higher reinforcement in this top reinforcement. Why? The moment will be higher, so the reinforcement will be higher. I cut my second B cross section. The B cross section, the moment will be higher in bottom section. The moment will be higher in bottom section. So I provide the higher dia in bottom section. Then go for your C section. Cut this C section. This is our C section, but the moment higher in compression zone. This zone moment is higher in compression zone. So I provide the extra bars for my compression zone. Top zone. Okay, top zone I provided. Bottom zone only extra bars. Okay, only extra bars will be provided the compression zone, tension zone, and all of us. Now we'll see this difference. Simply supported and fixed beam. Simply supported only one moment, and a continuous fixed beam. It have three moments in single beam. Another one, the simply supported, no moments will be transferred to column, but is the fixed beam. The moment this moment is transferred to column. The not no moment will be transferred is a transfer to columns. Okay, this is a difference, main difference. Simply supported and fixed end. Okay. Now the first concept is a bending moment, and then shear also. Shear also same like that. This is shear force. This is shear. Then this is our shear diagram. The shear is a 0 for your center post. Why the shear will be high in this corner and this corner? I simply draw my one longitudinal section of the beams. Okay, I draw this longitudinal section of the beam. This is our shear cracks. This is our shear cracks. Shear cracks only forms in one third of the corners. Okay, shear cracks will be formed in one third of the corners. So it will be higher in this corner. Only shear value will be high. The center portion, no shear cracks will be comes. So center will be 0. This is the concept for shear force diagram. Understand? This is shear force. So why the shear force in this direction is high? The cracks will be formed. So shear will be high. The center portion, no cracks will be formed. So shear value is 0. This is the main concept for your shear force diagram. I tell you how to provide the reinforcement for shear and then bending moment and all the things. The next one is a reaction. The what is meant by reaction? You studied that RA RB, right? RA RB. What is meant by reaction? Nothing but the beam load transfer to columns. Okay, the beam load transfer to column, that is called RA RB. Nothing but RA RB. The RA RB is the beam load. We are acting on the beam load. This is our UDL load acting on this beam. The beam load transfer to column, that is called RA RB. You see this difference. What in by bending moment and shear force reaction? You already studied in MOS. This is a basic concept for your beam design. One is the simply supported, and then another one is a fixed beam. Shear are same like that. Okay, shear force are same like that. The reaction means the column load, the beam total load transfer to your columns. Okay, this is the first things to understand the simply supported beams and fixed end beams. Okay, the next step is the analyze steps. Okay, next the basic I tell you what is meant by bending moment and that all. Next one is the analyze steps. Okay, next one is the analyze steps. Step one. Step one. The next how to find the sizes for your beam. Sizes for your beams. Okay, how to find the sizes for your beams. The first thing is the formula is 1 by 10 to 1 by sorry L by 60 to L by 10 to L by 16. This is a formula to find out the depth. Okay, formula to find out the depth. Wall is a sorry breadth. The breadth is equal to wall thickness. Okay, the beam breadth is equal to wall thickness. That is a concept. My wall thickness is at 230. So this is our cross section for your beam. So I provided the 230 for my cross section. Then how to find out my beam depth? How to find out my beam depth? The one is the formula, another one is the thumb rule is there. Thumb rule. Thumb rule is the 1 feet of the beam equal to 1 inch of the depth. Okay, this is a thumb rule. You know the thumb rule you're using on this field also. 1 feet of the beam equal to 1 inch depth. I take the width is equal to wall thickness. Okay, equal to wall thickness. I take this 230. Then how to find my depth? This is my span. I simply take my span is a 10 feet. I simply take my span of the beam is 10 feet. This my span is a 10 feet. 10 feet equal to 10 inch. 10 feet equal to 10 inch. So I provide minimum 1 inch. So I provide 9 inch. 9 inch means 230 mm. So, okay, 230 mm. So I find the depth for 230 mm into 230 mm. The next beam. The next beam is this beam is distance is 12 feet. Then how to find the depth for your beam? How to find the depth? Same procedure. Go to 12 feet. 12 feet equal to 12 inch. Okay, 12 inch. 12 inch is a 300 mm. So I find the 300 mm for my depth. Now it's clear. This is thumb rule. Using on this field also, design also. So all are trial and error method. Okay, this all are. Once you increase the steel reinforcement, you will decrease the concrete size. But I increase my concrete size, you reduce the steel. That is a concept. Okay. Once I increase my size of my concrete, so I decrease the reinforcement. Okay, this is a concept. I will increase my reinforcement, you will be decrease the concrete. That is the concept for your structures. So this is a main advantage for your thumb rule to calculate the depth. 1 feet equal to 1 inches. My beam is a 12 feet. 12 feet equal to 12 inches. Is a 300 mm. I found out the 300 mm for my depth. Okay. This is the first step to calculating the depth for your beam. Is a first step. Simply go for my beam depth is a 230 into 300. Okay. Capital depth you calculated the dia of bar on the others covers all of us. You will be calculated the depth. The next one is the main step 2. The step 1 is the depth calculations. Okay. Depth calculation, the maximum you will be using thumb rule, it will be pass. The step 2. The step 2 is a load calculation for your beams. Okay. The step 2 is a load calculation. Step 2 is a load calculation for your beam. First step is a depth calculation, overall depth. The second step is a load calculation. The load calculation means you consider as the what are the need to consider the load calculations. Okay, what are the consider as a load? One is the end condition. First, what type of end? Simply supported, or another one, what type of end? Next one is a span type. The next one is a span type. The next, what type of span, and load type, and section also. Section, that type of, you will be sorry, this is a categorization of the beam. Sorry, this is a categorization of the beam. The load calculation, what are the loads you will be considered? Okay, I tell about this is a categorization. The first one is the slab load. Slab to beam load you consider as a slab to beam load. The second one is a self height of the beam. Okay, second is a self height of the beam. Self height of the beam. The next one is a third one. Third one is a brick load. Okay, third one is a brick load. The fourth one is the concentration load. The fourth one is a concentration or point load. Concentration or point load. The point load means sometimes the secondary beam will be acting on this main beam. So it is a point load. The first load is a slab to beam load. Then second one is you calculating the self height of the beam. The next one is a brick load. Next one is a point load. Okay. Then how to calculate at the slab load, slab to beam? I already calculated my previous part one. The slab to beam load per meter is a 12.5 kilonewton per meter. My slab to beam load is a slab to beam load. I already calculated in part one. I calculate is a 12.5. The next one self weight. The self weight is a length into breadth into unit weight. Length into breadth into my 0.23 into zero point 0.3 into 25. I will calculate my self weight for my beam. 0.23 into zero point 0.3 into 25. I simply calculated my self weight. This automatically calculated the 1.725 kilonewton per meter. Okay, this is my self weight for my beam. You converted as a volume. You calculated the self weight for my beam. The next load. Next load you will be calculated the brick load. So okay, next one is a brick load. The brick load is a maximum load for this structure. Okay, understand this concept. The brick load is a maximum load. Then how to calculate the brick load for this structure? I using so many types of bricks in our field, right? So many types, fly ash bricks, hollow bricks, and engineering bricks. So many types are there. I am using engineering bricks. Okay, I am using engineering bricks. I am using engineering bricks. I take this value for 20.25 kilonewton per meter cube. Okay, this is my value for 20.25 kilonewton per meter cube. Then how to take my engineering brick value? I taken from IS 875 part 1. Okay, yesterday I tell about how to take the self weight for all materials. You take that IS 875 part 1. Okay, I take this engineer bricks, all the bricks are available. You take this 20.25. Then how to convert the kilonewton per meter, kilonewton per unit weight. This is a conversion formula. Unit weight into wall thickness. Okay, wall thickness into meter per meter is a 1 meter into height of the wall. This is a formula. Okay, height of the wall, the first into unit weight into wall thickness into per meter height of the wall. That is the formula for calculating the brick load. First my unit weight is a 0.25. So my wall thickness 0.23 into per meter. Then height, the height will be, this is our I calculated, this is my floor level, this is a roof level. So okay, this is our floor level, this is a roof level. The height is a 3 meter. My beam depth is a 300 mm. So okay, 300 mm. So minus your beam depth. Minus your beam depth means my total height is a 3 meter minus zero point 0.3 beam depth. So totally my height is a zero point 0.7. Save your bricks. That is the concept. Save your bricks means you minus the height minus brick depth. Okay. Simple. Your height of the building is a total height is a 3 meter. Okay. This is our bottom. This is our top. This is our beam depth is a zero point 0.3. Total height is a 3 meters. So that's only brick area. This is a no brick area. So total height is a 3 minus zero point 0.3 equal to 2.7 meter height for my brick calculation. So I provided the 20.25 into 0.23 into 1 into 2.7. Totally my brick per meter for my load brick load is 12.57 kilonewton per meter. This is my brick load 12.57 kilonewton per meter. Now it's clear. The first load directly slab load. Yesterday we'll discuss. The next load is a self weight for your beam. The next load is a brick load. The brick loads are, this is the procedure. Unit weight into wall thickness into height of 1 per meter height of the wall. The unit weight is taken from IS 875 part 1. Then you go for, sometimes the wall thickness is a 0.23. Based on your, you go for 0.3 or 0.35 based on your wall thickness into height. Height is a total building minus your beam depth. Totally you taken 2.7 meter for. So simply calculated 20.25 into 0.3 into 1 into total height is a 12.25 per meter. The next load is a point load. Sometimes acting on your point load means secondary beam. The secondary beam acting on this main beam, it acts on the point load. So I approximately calculate, but sometimes I approximately take the 15 kilonewtons. Okay, the 15 kilonewton. It's like sometimes the point load will be acting on only kilonewtons. Okay, understand it. Then this is my total load. Okay, this is my total load. I take this, my total load is the total load. I take this to 12.5, 13, and then 13 and 35. Okay, approximately I take this kilonewton per meter 35. I take this 35 kilonewton per meter. This is the load calculation for your beam. The one is the first step is the depth calculation. The second step is the load transfer to beam. Yesterday we'll discuss about. The next one is the self weight of the beam. It will be calculated. Next one is a brick load. The brick load also calculated. Unit weight wall thickness into height of the wall. It will be minus for beam depth. Next one point load. It's totally added. Total load is a my 35, approximately 35. Our next step is the next step you calculate the ultimate load into 1.5. Okay. The next step you will be calculated into 1.5, 35 into 1.5. This is our step 2 calculations. Okay. This is our step 2. Understand that. The step 1 is a depth calculation. The step 2 is a load calculation. You know that yield line theory, then you calculated the load, slab load to beams. Okay. You do not know the yield line theory at all. It's wrong with on this beam calculations. Okay. Then the brick loads are taken from IS 875 part 1. Then you go for this. Finally, I take this value 35 into 1.5 by total load. Okay, this is step 2 is a calculating for your beam loads. Okay, now it's clear how to calculate the beam loads for your area. The next step is a step 3. The step 3 is the bending moment calculations. Okay. Step 3 is the bending moment and shear force. The shear force is no problem. Bending moment. Okay. This is some difference is the bending moment for simply supported beams. Okay. The bending moment for simply supported and fixed beams. Okay. Fixed beams. You calculated the bending moment is directly provided a WL square by 8. You will be calculated the bending moment calculations. Okay. Once again, I will check the correct WL square by 8 or 12 for calculation. You want? WL square by 12. Sorry. W your bending moment formula is a W L square by 12. For simply supported beams, will be calculated the value for bending moment formula is a W L square by 12. It's an easy one. You are simply supported means you simply calculated W L square by 4. Then you go for check this section and then you calculated the AST and the reinforcement at all. The next step is a main step. This is the formula for WL square by 12. Okay, for simply supported. Then you go for fixed beams. Okay, fixed beam. There is a main method. The fixed beam, you go for normal analysis and not used. You go for substitute frame method. To analyze your fixed beam for manual condition, you go for substitute frame method. This is a method of analysis. Okay, this method is the substitute frame method. First method is the substitute frame method. Substitute frame. There are three methods are there. 1, 2, 3. I taking the first method. Okay. You analyze in your fixed beam moment. You go for substitute frame method. It's detailedly given in IS 456 also. It's a code books. It will be given in so what is the substitute frame method and all. You go for the fixed beam. You choose for substitute frame method. The mainly you choose it substitute frame method. Okay, I choose the fixed beam. I choose the substitute frame method. Then this is a method. Then analyze. I'm going to analyze means I choose for moment distribution method for my fixed beams. Okay, moment distribution method. Moment distribution method. Okay, this is a analyze. This is a method. This is a substitution frame is a method. Then this is the analyze. This method I go to analyze for so many analyses are there, right? Moment distribution method, method, so many methods are there. I choose for moment distribution method for analyzing for my fixed end moments. This is simply support, it's a only one formula. This is a fixed end. You calculated the this one moment, 2, 3. So I am choosing substitute frame method. Analyze, go for moment distribution method. This is the correct procedure to analyze the fixed beam. Okay, moment distribution method. There are so many methods are there. Slope deflection method, strain energy method, Ennis method, and so many methods are there that I using moment distribution method for manual. The softwares are doing the softwares are what software methods. Softwares are what method to analyze this full building software. The StatPro will do for matrix methods. Okay, the StatPro will do for matrix method. ETABS will do for finite element methods. Okay, finite element methods. StatPro will do for matrix method. ETABS will do for finite element methods. I will go for moment substitute frame method. In analyze, I go for moment distribution method. I tell about how to analyze the frame in moment distribution methods. Okay. The next one, moment distribution method. Another one, I tell about some span distance of the beams also. Spanning distance. Spanning distance of the beams. Distance of the beams. Okay, spanning distance of the beams, and then go for the moment distribution methods. Okay, then I go for three moment distribution method. I tell about some spanning distance of the beam. There are two types are there. One is a rectangular and a flanged. Okay, one is a rectangular beam, another one is a flanged beam, another one is a flanged beam. There are two beams are available. Type one is a rectangular beam, another one is a flanged beam. You go for rectangular beam, two types is there. One is a singly reinforced beam, another one is a doubly reinforced beam. Okay, rectangular section means one is a singly reinforced beam, another one is a doubly reinforced beams for your section. Okay, go for flanged beam. T beam is available. Okay, T beam, another one is a L beam. You design for based on your moment condition. You go for rectangular beam is a singly reinforced beam, and a doubly reinforced flanged beam means you go for T beam or L beam. The spanning condition for your rectangular and flanged beams. Okay, rectangular flanged beam. Flanged beam. You go for a fixed. I tell about fixed continuous. Okay, I tell about fixed continuous. The fixed continue means you go for 8 meters span also. Flanged means 12 meter. You go for longer span. You analyze as a T beam. Is a economical one. Okay, you analyze as a T beam. The 8 meter means 8 into 3.28. You convert approximately 21 feet. You will go for WR singly in this rectangle. But you have 36 feet. You go for fixed continuous beam in 12 meters. It is a main advantage for your T beam. The next condition, simply support. You design as a simply support. You go for rectangular as a 6 meter. Then flanged T beam as a 10 meters. Okay. Then you go for cantilever. You design as a cantilever. You go for rectangular section as a 3 meter. Then flanged section as a 5 meter. This is the main spanning distance from beams. Okay. The rectangular you go for fixed or continuous. The rectangular means 8 meter. The flanged is a 12 meter. Only the flanged section is the economical is a 12 meter. Then simply supported you go for 6 meter. The flanged is a 10 meter. Another 3 meter. This is the main things. Okay. The next one go to moment calculation for this beams. I already discussed about the simply supported means WL square by 12. Another go for fixed continuous substitute frame method used for three moment theorems. Okay, distribution method. I will simply draw the one frame in this buildings. Okay, I simply draw the one frame. How to take this section and at all. So again, I simply saw this one section. I cut this section and then I calculated the how to calculate the moment. values, then how to apply the check the stat row, that all. Okay, first of all, I simply draw the one G plus 3 floor. Okay, in 2D, G plus 3. This is the center span. I simply draw this. This is the top floor. This is the next floor. This is the next floor. Is 1, 2, 3, 4 floors. Totally 4 floors. Yeah, this is the ground level. This is the ground level. Okay, this is our ground level. I mentioned this distance for this frame. How to analyze the fixed frame in moment distribution method. This is our 2D frame. I simply mentioned this is a column number. This is a column number. I simply mention this column number for this area. Then I put this distance 6.2 meter. This is a 8.4 meter. Then some point load. The point load acting on this all floors. The point load is acting on this 2.2 meters. Okay, 2.2 meters. This beam distance is a 6.2. Then this total distance is a 8.4. The point load acting on this 2.2. Then I put this, mention this name 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, this is no problem. I tell about the 15. Then this is our 2D frame. Then how to analyze this moment distribution method in this frame? First of all, I cut this section. I take this section. This is the top floor. This is mentioned as a top floor. This is mentioned as a second floor or third floor. This is a middle floor. I mentioned this middle floor. This is a bottom floor. This is a bottom floor. I simply cut this middle floor. Okay. I simply cut this middle floor. See, automatically this is my cut section. I cut this middle floor. This automatically I cut this middle floor. I fix this number 4, 5, 6. This is also fixed end. All are fixed end, right? To mention this, all are fixed end. This automatically the all are fixed end. This automatically I fixed the all are fixed end. Then go to see this. I put this number also 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, this is the frame structure. Then you calculated this moment for this condition. This same moment will be calculated on this manual calculation. Okay, you calculated the 4, 5 moment and 5, 6 moment also. This moment and column moment also. Then you calculated the column moment also. This is I take this cut section for this floor. I calculated the 4 to 5 moments and 5 to 6 moments. And using moment distribution method, I calculated this moment. Okay. Then load acting on this area. Load 4 to 5. The 4 to 5 it's act on this 39 kilonewton per meter load. Then this beam, this is a 8.4 meter. This load is acting on this 13 kilonewton per meter. Okay, 13 kilometer. Then point load, approximately I take this point load is a 35 kilometer. The span is a 6.2 meter. This is a 8.4 meter. The center portion is a 2.2. Okay, a 2.2. Now it's clear. The load is I taken from this load. This load is the totally this distance is a 13.9. This is our 13 kilonewton. Then 6.2, 8.4. Okay, this is the first. I draw this another one page. So I simply draw this another one page. This is our frame, right? This is our frame. This is our section. This is a 3 section. Then go to create your fixed end. This is a fixed end. This is also fixed end. This is also fixed end. This is center portion. This is a bottom portion. This is also fixed end. This is also fixed end. Then this is our length is a 6.2. This is a 8.4. Then point load acting on this 2.2 meter. 2.2 meter. This beam load acting on this how much kilonewton per meter? 39 kilonewton per meter. This load is acting on this 13 kilonewton per meters. Okay, 13 kilonewton per meter. Then column height. This is our column height 3.35. 3.35. Approximately I take this, my beam size is 230 into 500 mm. So, okay, 230 into 500. I take this column size also 230 into 500 mm. I take this approximate size for my beam and column also. Okay, this is my load case 1. Okay, this is my load case 1. I calculated 3 load cases. This is our load case 1. I calculated the 3 load cases. Load case 1, load case 2, load case 3. Why I am choosing 3 load cases? First of all, this is my first load case. I acting on this 39 this area and 13 this area. My second load case, this I take this portion only. This is my second load case. Okay, this is my second load case. I put the this side load, minimum load into 13, maximum load is put on this side 39. Then the point load are same direction. I put this heavy. This is 6.2, 8.4. Okay, this is a load case 2. The next one is a load case 3. This next load case is a 3. Same like that. The load case 3, I give the higher load. I give the higher load for two sides 39. This is also 39. Is our point load is a 72. You are asking why I give the higher load, then I take this bending moment at all. The span is a difference. So you know the stability structure theory. The stability structure means your beam will be failure. Suppose the 6.2 beam will be failure means the total load transfer to nearby the beam. That is called stability structures. Okay, this beam 6.2 beam will be failure. This beam load will be transferred to nearby 8.4 meter beam. So I taken into 3 load case. Which load case I give the maximum moment? I will take and design for my section. Okay, the first load case I give this same as a second load case. I change into value, and third load case I give the maximum value. I calculated the 3 moment distributions and 3 moments for your moments and 3 shear force. I take this maximum value, then I go for this. Then I take this rectangular section or T section and others. Okay, this is a procedure. The first procedure, you take this cross section for moment distribution method. You take the 3 load cases. First stability structure. Once you failure for your beam, the beam load will be transferred to another beam. Structure will be safe, not collapsed. But you do not using this method, sometimes beam will be failure, the structure will be failure. That condition it will be using for stability structure theory. I am choosing, I take this 3 load cases. I give this normal load cases. Second load, I changing the value this side to that side. Then load case 3, I give the higher value for. Then next procedure, I calculated the moment values. Okay. Next step 4 also. Step 4 also I calculating the moment values. Okay, then I calculating the moment values. The first step is a fixed end moment. Same procedure for moment distribution is using for, you take the structural analysis book. Structural analysis, you refer that. Okay, you take the structural analysis, then you refer and calculate this all the values once. Already I tell that the 3 subjects are main. The first subject will be completed, MOS and other. The second one is the structural analysis. The structural analysis, the first part, you calculate the fixed end. My fixed end is a, I simply calculated my fixed end for these conditions. The first one is I calculated fixed end. This is my moment. See this. Yeah, 4 5. The 4 5 is this moment. This to this. This is a 4 5 6, right? This is a 4 5. I take this maximum moment and then minimum. I take this minimum is a FP 5 4. Okay. This is a 5 4. My formula is a W L square by 12. The maximum I take this 39. The minimum I take this 13. You calculated this value also. The first condition is a fixed end supports. I take this. Okay, I go for this one new page. Next, the first step is a fixed end moment. Okay, fixed end moment. I go for this. Yeah, 4 5. 4 5. The formula is WL square by 12. the maximums. Okay, this is the maximum. I simply apply the 39, then go for Fe54. Then same procedure, WL square by 12, then apply the 13 value. You take this result per kilonewton per meter. The next beam. This is the two beams are available, right? This is the two beams are available. This is 0.2 meter beam. The another beam is a 8.4 meter beam. The point load will be acting on this. I go for next beam. The next beam same like that, 5 6. This is a 4 5. I will be calculated the fixed end in this formula. Next 5 6. This is a 5 6. I go for 5 6. The 5 6 maximum. The 5 6 maximum, simple same procedure. WL square by 12 plus WAB square by L square. AB means it's acting on this point load. So I calculated the formula WA 2.2. D is the minimum distance. L is the total distance. Then maximum. Next one is a 6 5. You go for 6 5 as the same formula. WL square by 12 plus W A square B divided by L square. You calculated the value for maximum in this fixed end moment. You calculated this fixed end moment values. Then minimum moment. You go for minimum moment for FE 56 minimum value. This value you apply for your 36. Okay, this value, sorry, 39. You will be apply the 39 for maximum. You go for minimum, you apply the 13. 5 6 same procedure, WL square by 12 plus same formula, but the value will change. You go for maximum value, you take this 39. You go for minimum value, you go for 13. The point load you take a 75. Okay, the point load you take the 75. The first step, you calculated the fixed end moment. This value fixed end, this fixed end, this fixed end, and this fixed end. Okay, the four fixed end are there. You calculate the first step is a fixed end moment. Okay, fixed end moment. I take this maximum value and minimum value. The next step is the distribution factor. The second step is the distribution factor. Once you take the distribution factor, then go for moment distribution tables. When you calculated the distribution factor, then you go for the distribution table and attals. Okay. Next one, distribution table. How to calculate the distribution factor for this one distribution factor? Next step is a factor. I simply draw this table. First, joint conditions. Okay, the first one is a joint. Second one is a member. Second one is a member. Next one is a response factor, rotation stiffness factor, RSF. Rotation stiffness factor, this is the main one. Okay, rotation stiffness factor. First one is a joint. Okay, first one is a joint. How many joints are there in this field? 4 5 6. 4 5 6 joints are there. Members, this side is our numbers are available, right? This numbers and bottom number, top number and bottom number. I simply take this 4 5 4 1 4 7, then 5 5 4 5 6 5 2 5 8, then 6, go to 6 6 5 6 3 6 9. The joints are 6 5 is this number, partition by 6 3 is the top column number, this number 6 5, and 6 9 also bottom number. Okay, take this joint numbers. The next one is a rotation stiffness factor. This is the main one. You take the joint and the members are easy. Then how to calculate the rotation stiffness factor? Rotation stiffness factor is the main one. Okay, rotation stiffness factor is the size of your body. The rotation stiffness factor, you will be calculated the rotation size of your body. Then there is a formula, means rotation stiffness formula is a I by L. So okay, rotation stiffness formula is a is our rotation stiffness formula equal to I by L. I is the moment of inertia, shape of the body. Okay, moment of inertia is the shape of the body. Simply you will be calculated the shape of the body is a moment of inertia, I. How to calculate the I value? I equal to BD cube. Okay, I go for this another one page. Rotation stiffness factor. Rotation stiffness factor equal to I by L. I is the moment of inertia. Okay, I is the moment of inertia of force. Moment of inertia will be calculated the I equal to BD cube by 12. Okay, BD cube by 12 is your moment of inertia. The B and D, already I assumed that my breadth and depth 230 into 500 for my beam size. 230 into 500 for my beam size. I simply apply for my moment of inertia. This is automatically I apply the 230 into 500 divided by 12. I simply calculated the I value. Then rotation stiffness value, you simply apply the I values. Okay, simply apply the I values. Then you go divided by length value. Our length is the, you taken the any length. My length is the 6.2. You simply calculated the simply calculated the which value? Sum of values. Okay, sum of value. Then finally you calculated the distribution value, sum of value. You simply calculated the sum of value, response pattern and sum of value. Then you calculated the BD cube by 12. That value provided by length, you will be automatically calculated the RSF value, rotation stiffness value. Now it's understand. First one is a member. You calculated number, joint, then our rotation stiffness factor. There is a formula is a I by L. I is the moment of inertia. L is the span. You simply calculated the all the rotation factor. Then go to finally you calculated sum of. You will be add it. Then go to you calculate this distribution factor. That is a calculating adding and minus only. This two only. That is a easy one. But this is the main one. Rotation stiffness factor. You based on your beam and the column size. Okay, based on you go for beam design, you take this beam size. Beam size is 230 by 300. I go for column size 230 by 450. This is the condition for your inertia and body size, all of us. I simply take this value, my value for rotation stiffness 0.774, 0.75, 0.75. This is the main one. Finally I taken into distribution factor. So finally I calculated the distribution factor. Approximately I take this, my distribution factor value is 0.325, then 0.35 and 0.325. This is our distribution factors. Okay, so I will once again I will show that only one in clear page. Okay, only one. First of all, joint member. Okay, I'll take only one joint. I simply go for joint 4 member, 41, 45 and 47. RSF, I tell about the formula. I by L, I equal to BD cube by 12. Okay, I calculated this value 0.715. Then this is a different value 77, different span and different size. It's automatically it's changed the same values or different value. See this two are same value. Then this is a different value. This is the beam position. Okay, understand, this is the beam position. This is the column positions. This is a column position. The column are same sizes and same height, so it will be same value. But the beam is single, so beam is a different span and a different size, so this value will be different. The next one is a sum of, so you add that all the values. Okay, sum of you all that add the values, then calculated the distribution factor. The finally you calculated the distribution factor for your area. Finally you calculated the 0.325 for your distribution factor. Then go to this value 0.35, then 0.325. This is a method to calculating the response reduction factor and sum of and distributions. Okay, the next one, this is over. I calculated the distribution factor for this all the three cases, not only one cases, all the three cases. Next one is a moment distribution. The next step is a moment distribution. I simply go for my moment distribution. This is a long procedure. The next I go for this moment distribution. Okay, next I go for this moment distribution. The moment distribution has same columns. The first is the joint values. The first is the joint. I simply draw this joint numbers 4, 5, 6. Okay, 4, 5, 6. Then member. This is a member. Member I draw this 4. 4 number I provide the column number. Then 4, 5. The 4, 5 is a beam number. column is I tell about this is our end is this one. This is our beam. Okay, this is our beam is a 4 5 4 5. This two are there. This is a column moment. Okay, this is a 4 5 is a column moment for this condition. This go for 5. Fifth joint. Fifth joint also two number 5 4 column 5 6. See this is our another number. See this is another number. The 5 4 5 4 is this beam moment and the 5 6 is this beam moment. The column is a center portion, so column is there. This moment is a column moment, so I mentioned this column. Then go to 6. The 6 also same like that, 6 5 and then column moment 6 5. This moment is a 6 and 5. This is the column moment, so I provided this column moment. Then go for distribution factor. I already calculated the distribution factor for this areas. Okay, I simply go for distribution factor, then I go for finite element method, then calculated the carryover and balance. Okay, you go for carryover and balance for 3 times. It's take a accurate values. Okay, understand this. You take this carryover and balance, it go for 3 times. You take this accurate value. So finally you calculated the moments for your sum. Okay, finally you calculated the moment for your column moment for 82.3. Then beam moment is a 82. Then another 5 4 is a 42.51. Then approximately I take this all the moments will calculated. Understand this one's concept. You compare with the span moment and the support moments. The support moment will be higher. Okay, the span moment will be less. It is small concept. Okay, you compare with the span moment and the support moment. The support moment will be higher. The finally I go to moment distribution method. The finally I take this moment values. Okay, finally I take this column moments. This column, this moment I will be calculated the column moment. This end moment I will be calculated this end moment. This end moment. So now itself I using the moment distribution method, I only calculated the column moment, and end moment also. Then how to calculate the center moments and shear force also. Shear force also same like that. You calculated the shear force. The shear force also same like that. The another you consider the another design. First you calculated the bending moment, shear and reactions. Then you calculated the easily calculated the bending and shear also. This only you calculated the bending, then you take the shear also. Okay, then you calculate the shear also. I calculated the one shear value. I simply calculated the shear for 4 5 beams. Okay, 4 to 5 I calculated this shear value. This shear value 4 to 5 I calculated the 4 to 5. This is our formula is a load. My formula is a 39 total load 6 point into divided by 2. WL by 2 is a shear formula. Okay, shear formula. I simply click this WL by 2 minus our bending moment. I based on the bending moment I will be calculated the shear value. So this is our bending shear value WL by 2. Then I go for bending moment. My bending moment value is 142.51 minus 82.63 divided by 6.2. 6.2 is this span distance 6.2. The bending moment is this distance 4 5 and 5 4 bending moment. You minus this 4 5 and bending moment, then you finally calculated the shear value for this all the beam centers. Okay, now it's clear how to calculate the shear values. You calculated the moment distribution, then go for shear value, then finally you calculated the shears. Then how to calculate the center moment? Then you go this method you calculated only end moment. Then how to calculate the center moment value? How to calculate the center moment? You go for this formula. I calculated the center moment. The span 4 5. The 4 5 is I calculated center moment. Then you take the shear value. Calculated the shear value 112 point divided by total load. Then you take the point of contraflexion. Which portion will be acting on your center portion of your moment? Okay, this is a center portion. You will be calculated the distance from this point of contraflexion. Okay, this distance is h2. This distance is a x. This is the point of contraflexion. I will be calculated my distance 5 4. Then finally you calculated the moment for your center portion. Okay, this is the main procedure to calculating your shear moment and center moment also. There are so many procedures are there. I tell about simple basics. This is the main procedure to calculating the values. Okay, this is the main procedure to calculating the values. Then you go for next. Then you calculated the three load cases: load case 1, load case 2, load case 3. Same as you calculate the moment distribution, you apply the three moment value. Then finally you take the higher values. Higher values compare with the three moment, which is the higher value. You take this higher value for moment and shear also. Finally, you take the moment and shear also in higher values for your designs. Okay, this is I simply take this higher values. Then finally, how to design the your beams. Okay, how to design your beam. This is a method to manually analyzing your fixed beams. First of all, you go to moment distribution method. You finally analyze them. Then how to design your beam. The step I simply create a one table. First one is a descriptions. Okay, first one is a description. Then my joint 4 mid span, then fifth mid-span, then sixth. Next one is a condition, end condition. The next one is the end conditions. Okay, step 2, the end condition. End condition, the joint 4. The joint 4 is a fixed, right? Or joint 4 is a fixed. The 5 is a continuous. The 5 is a continuous. Then joint 6 is a fixed. So I mentioned this joint 4 and joint 6 are fixed. The 5 is a continuous. Then span. The next one is a span for your beam. The center one, the center portion mid span 6200 mm. This is the 6400 mm. Okay. First step is a joint, then second step is a your joint 4 is a fixed or continuous. Then next one is a span moment. You simply enter the span moment. The next step is a section. You assume as your beam section 230 by 500, etc. Then fourth step. The fourth step is a load. What are the loads acting on your beam? I 13, our point load is a 75. The next step, the step 5 is the bending moment. The bending moment is simply supported. You go for WL square by 12. At the fixed end, you calculate the moment distribution value. Directly enter your moment distribution value for your this type of conditions. I simply taken this moment distribution value. I simply entered this. I calculated this whole value for this moment distribution method. The next method is a mu max. Mu max. I simply calculated my mu max is a smaller. This also all the mu max are smaller. See this 122, 122. Then my moment is a 82, but mu max is a 22, so it's a smaller. So I design as a singly reinforced. This is the 76 122. These are also simply as a singly reinforced, but it's a 122, but it's a 209. So I design as a doubly reinforced. This is a moment is a 122. This is a 163. 132 160. This is also a design as a double A. This is a section type. Okay, how to mention your section type based on your moment value, then maximum moment. The maximum 122 is a minimum, so singly this portion is a singly, this portion is a double A, this portion is a double A. Then next step is a based on your reinforcement and all the values. Okay, next one is a simply you calculated the AST values and all the things for your buildings. Now it's clear how to calculate. This is why I tell about only small things, not a big things. This is the procedure to calculate the moments distribution and all the things also. Then what are the texts are available? What are the main themes and other for your slab also? What is the minimum distance for your beam? Once again. Yeah. This is the beams and minimum reinforcement and maximum all the things for your beam sections. First one is the minimum tension reinforcement for your beam. What is the formula for minimum tension as per IS 456? Minimum tension reinforcement formulas. Reinforcement detailing. Okay. Reinforcement detailing. Reinforcement detailing. The first step is the first one. What is the minimum tension reinforcement for your beams? Okay, tension reinforcement for your beam. The first formula is this: AST by BD 0.87, sorry, 0.85 divided by Fy. This is the formula for you calculating the minimum tensile reinforcement for your beams. Okay, this is the formula. Is available in IS 456. This is the minimum tension reinforcement for your beam. AST BD 0.85 divided by Fy. What is the maximum reinforcement? Next one is the maximum reinforcement. Maximum reinforcement is a for compression and tension. Compression. PC is a compression. PT is a tension reinforcement. Okay. The W have a two reinforcement are there, compression and tension also. Is I simply go for I calculate the tension reinforcement, maximum reinforcement 100 AST into BD. This is my tension reinforcement, maximum reinforcement percentage for my tension. For compression, same as a 100 ASC, compression AST, then same as a BD. The section are same, the AST are different. This is a AST, tension reinforcement percentage. This is the compression reinforcement percentage for your doubly reinforcement for maximum reinforcement. The next one is a side reinforcement. Next one is a side reinforcement for your beam. Sometimes you will go for a single or double. You provide the top and bottom reinforcement only. Provide the top and bottom reinforcement only. The when you provided the side reinforcement, this is our side reinforcement. Is automatically it's provided the side reinforcement. The when you provided the side reinforcement, your beam will be more than 750 mm exceed, you will be provided the side reinforcement. Okay, your beam will be maximum, you provided the 750 mm, you provided the side reinforcement. The next one is a minimum shear reinforcement. Minimum shear reinforcement for your beam. This formula is available in IS 456 also. This formula is you calculated the checks for your minimum shear reinforcement for your beams. The stirrups are not exceed. Stirrups are not exceed 0.75 D or 300 mm. Okay. Stirrups are not exceed. Whichever is smaller, you will be take the minimum shear reinforcement. Next condition is the spacing of main steel. The next one is the spacing of main steel. Next one is the spacing of main steels. Okay. The spacing of main steel is that the bars shall not greater than the bars, the bars shall not greater than dia of bars. First is a dia of bars, second is a 20 mm aggregate, not greater than 20 mm plus 5 or 25 mm aggregate. Okay, 25 mm aggregate not greater than bar spacing, the spacing not greater than 25 mm. The next also 25 mm, 20 or 25 mm spacing for your bar sizes. Okay. Next one also cover. The cover is based on 20 mm. Is based on your exposure conditions. Okay. Based on your exposure condition for your area. The next one, this is the basic condition formulas for your reinforcement, the beam reinforcement. The next of all, I tell about some small diagrams about reinforcement detailing. The reinforcement detailing, first of all, I tell about continuous fixed beam reinforcement detailing. Continuous fixed beam. So okay, this is our continuous fixed beam. I draw this one longitudinal beams. Okay, this is a one longitudinal beam. Then go for I take this. This is our continuous beam. See this. This is our continuous beam. To it is this two rods. These two rods are minimum reinforcement. Okay, these two rods are minimum reinforcement for compression zone, and this is a minimum reinforcement for tension zone. Okay, This is all the formulas are available in IS 456. Okay, this is the IS 456. This is the compression. This is a continuous beam. This is the compression for minimum reinforcement for compression. The maximum I provide the minimum for two numbers of 16 mm dia. This is also I provided the two numbers of 16 mm dia for my tension also. Then another bar I provide the cutlement bar for this distance. Top and compression, this is also top based on your moment condition. See this, I provided the two numbers of 20 mm dia, two numbers of 20 mm dia in compression. In compression also I provided the four numbers of 20 mm 16 20 mm dia. This bar, this top also same like that, two numbers of 20 mm dia. The minimum reinforcement I provide the 16 numbers of two bars. Based on your moment, the cutlement bar will be I provided the two numbers on this top for two end and four numbers on this bottom. You know that cutlement distance, all of us you refer that SP34 code books. Okay, SP34 code books. You cut this section. This is the A section for this end. This is the B section. This is a B. This is the C section. I cut this cross section for my AA. This is my cross section for my AA section. This is my cross section. This is my top zones. Top zone I provided the four bars. See this automatically. This is a minimum two bars. Then this two bars. Totally four bars. The compression zone, bottom zone I provided only minimum reinforcement. Two number 16. This is the two number 20 mm 16 and two number 20 mm dia. This corner. Then go for I calculated the then BB. This is our BB section. This is our BB section. See, this is our BB section. Then go to, this is a minimum reinforcement. For this minimum reinforcement, I provided the 216. Then bottom, I provided the minimum 2. Then additional 4 also. See this 216. Then 420, all this B section. Then CC. Then go for CC. Simply click this CC section. This automatically you go for this CC section. Then go to same like that. In this bottom I have a four numbers. Then a minimum in this reinforcement it provided the two numbers 16 minimum. It's a two number 16. Then two number 20 for this bars. Okay. Next one is the stirrups. How to provide the stirrups? This is our longitudinal section. Then go for provide the stirrups, stirrup spacing. See this edge I provided the spacing. Then center portion I provided this end also. Why I like this end I will be reduce the spacing. This stirrup spacing I have provided the 120 mm. This center portion I have a 200 mm. Why? The shear will be high in this corner and this end. Center portion will be low. So I provided the stirrup spacing is lesser in two ends. Zero shear in mid. So I give the higher spacing in mid of the beam in stirrups. Okay, this is the main reason why the stirrups will be minimum spacing in two corners. The shear will be high. The mid portion why will be higher. This is same portions. Okay, this is a reinforcement for your continuous beam. The calculation for moment distribution. Then all of us it will be followed the moment distribution method. And another one is a redistribution. You know that the redistribution, one of the concept I tell about the only that concept only. Redistribution. Redistribution is that this is our beam. Okay, this is our beam is the this moment, this corner moment is redistribution into 15% of the moment is redistribution to center of the beams. Okay, center of the beam, that is called redistribution. Redistribution allowed for 15 to 20% for your beams. Redistribution means for simple example, this is our beam is there, right? I will draw. This is a 20, this is a 40 is there. I need this 20 beam I taken into 50%. For example, 5 kilonewton per meter moment I travel into center beam. The center beam is taken into 45 moment, but this corner is taken into less than 15. The corner will be less moment, the column moment also less, automatically size will be low, all the size will be low. This is the main uses for your moment distribution method, sorry, redistribution method. It's available in IS 456 also. Okay, so now it's clear how to design the beams in manually. You go for moment distribution method and reinforcement and all the things. Okay, so okay, now I complete the section, today's section for moment distribution and all the things for this slabs. Okay, I put this attendance form in this chat box. Please fill the chat box for your attendance. The it takes the 80 percentage. It says 6 days mandatory to attend. You get the certificate for this courses also. Okay. Okay, fine. Today we'll discuss about the columns also. How to take the effective length, short column and long column, and others also. Take the 4 basics values, reinforcement detail, then footing, then go for analysis, software analysis, how to analyze the same slab, beam, columns, all of us, etc. Okay. Okay. Once again, thank you all. Thank you. Please share your attendance and feedback also today's section. I hope you understand, you know that something about the manual calculation for your moment distribution method and all of it. This is a method to design your all the continuous beams and all the things. Okay. Okay. Once again, thank you all. Please fill this feedback form. The attendance will be mandatory for 80 percentage. Only you give the certificate. The feedback links only validity for 10 minutes. It automatically scores for 820. Only live participants will be give the certificates. Please fill the feedback forms and attendance also.